All right, so we're talking about limiting reagents. And just to bring it up front, a reagent and a reactant are pretty much the same thing. Subtle difference, but for our purposes, they're going to be the same. And really what it comes down to is this, that there are reactions that where one of the reactants is more than you need, or perhaps less than you need, but we'll get to that in a few minutes. So let's start with the idea. And we're going to start with a sandwich or some other food, but sandwich makes a really easy recipe to make, because if I have a recipe like that, 2 bread, 1 cheese, slice of cheese, making 1 sandwich, then if I were to have more of one ingredient or the other or both, or if I had 20 pieces of bread, I could potentially make 10 sandwiches. If I had 15 pieces of cheese, I could potentially make 15 sandwiches. But, and here's where we're getting to the point, if I had both of them at the same time, the 20 pieces of bread and the 15 cheese, I'm going to run out of bread and have leftover cheese. Now, the idea with limiting reagents is that the amount of product I can make, in this case a sandwich, is going to be limited by one of the ingredients, one of the reactants. Now if I take a reaction like this, fairly simple reaction, follows the same basic principle as the bread and the cheese to make a sandwich, but now of course I'm talking in terms of moles. If I was making those products and I had 2 moles of potassium, well, I could potentially make 1 mole of product. If I had 1.5 moles of sulfur, I could potentially make 1.5 moles of product. But if I had them there at the same time, then I'm limited by the amount of potassium. Now, I want to really emphasize this point right off the bat. Having more moles of potassium does not mean it is the one that's extra. The one with the fewer moles, in this case 1.5 moles, it's actually the one that I have extra of. I run out of potassium first because I need more of the potassium. Okay? But exactly the same thing with limiting reagents in chemistry as running out of ingredients in making sandwiches. Okay. If I had a reaction like this, and I want to emphasize again that we don't work with reactions in terms of moles, at least not right away, but that's what reactions do. Reactions operate in terms of numbers of moles. But if I had 5.3 moles of iron 3 oxide and 15.5 moles of carbon monoxide, now you might be thinking lots and lots of moles of carbon monoxide, it's got to be lots of there, but we have to do the math. So the job we're going to do is, in order to figure out which one is limiting, is we're going to divide them by the balancing number. And the way I like to think of this is, if I think of my reaction as operating in groups, all right, so I've got 1 of the iron 3 oxide, 3 of the carbon monoxide. All right, let's put them into groups of 1 and groups of 3s, and then I can figure out how many groups I have of each. So when I divide them by the balancing coefficients, I find out that I got 5.3 groups worth of the iron 3 oxide and 5.17 groups worth of the carbon monoxide. So I actually have less carbon monoxide than I would need because of the way it groups together. So the reagent with the smaller number here is going to be the limiting reagent. Well, how many moles of product could I make? Because ultimately that was the question, is not how do my ingredients work out, how do my reactants work out, but the question is really going to be about the products. Well, once I know which one is limiting, then I do the math with it. The other one, the one that's in excess, the one that I have extra of, the iron 3 oxide, doesn't matter. I can ignore that at this point because now I know that the carbon monoxide runs out first. So I do the math there, in this case just molar ratios, and I end up 10.3 moles of iron. Now, of course, we don't work like that. We work with masses. So we need to work our way toward that. So if I had this particular reaction, and now we're going to do a full limiting reagent question where I'm looking for a mass, and I'm starting with a mass. But I have 15.8 grams of aluminum chloride and 8.4 grams of magnesium oxide. I want to say it again for 2 reasons. One, the one with the smaller number of moles to start with is not necessarily the one that runs out first, but even more important, the one that is the smaller mass is completely irrelevant. Ignore the mass. Well, don't ignore the masses, but don't look at the masses and start to get an idea or a guess in your mind. Okay, job 1, calculate number of moles of each. Job 2 is what we were doing before, where we figure out the limiting reagent by dividing by the balancing numbers, and then doing stoichiometry with the one that's in limiting amounts. Okay, so in this case, I'm going to have my reaction, I'm going to have my masses, I'm going to divide each one by the molar mass. That's going to give me the number of moles. And again, you really need to pause this, look up the molar masses for each one of those things, and then, or determine the molar masses of each one of those things, so you know where those numbers come from. Okay, so now I've got numbers of moles, but again, I can't really work with those numbers of moles. What I need to do is put them into groups. So divide each one by the balancing numbers. So divide the aluminum chloride number by 2, divide by the magnesium oxide number by 3, and then I've got my groups. So turns out that the aluminum chloride is one that's in limiting because it has less groups possible for it. But again, think about the masses and so on, right? It's got to be to this point where I've done the division by the balancing numbers. Now I'm going to do the stoichiometry. Now I'm going to assume at this point that you're familiar enough with stoichiometry that you know how stoichiometry is going to work, where I take the mass of the known, the aluminum chloride in this point, turn that into a number of moles of aluminum chloride, turn that into a number of moles of aluminum oxide, and turn that into a mass of aluminum oxide, just following the stoichiometry pattern as we've always had it, getting us a final number of aluminum oxide that I can make. Okay, one for you to try, and I'm going to leave this with you, but it's going to be a very similar idea. What mass of water can be produced from 53 grams of ammonia, NH3, and 185 grams of oxygen, O2. Your plan of attack is going to be figure out the number of moles of each one, divide each one by the balancing coefficient that it has in front of it, and then doing stoichiometry with the one that is limiting. Now I want to say two things. One, this is really just stoichiometry with a few things on the front end. Two, because it is just stoichiometry with a few things on the front end, the most important thing here is the few things on the front end, because we've already done stoichiometry a fair bit at this point, and I'm hoping, expecting that you're kind of familiar with it. Okay. After that, it's just learning a few extra new steps at the beginning. All right, we'll talk to you another time.